Okay, we are on to our day 9 example. We're going to find this is more or less the same stuff we did in day 8. We're just making the problems a little bit more complex. So with this, what we've got going on is we have a sledding hill. And that sledding hill is a total length of 100 meters. It is set up at an angle of 30 degrees. This is terribly out of scale. And we have 2 sledders on the top. So we have a sledder that we're going to call sledder A. This guy is A. And we have a sledder at exactly the same point called sledder B. And both of these 2 are starting at rest. Velocity is equal to 0 at the top of the hill. We are asked, we are also given the values for the hill. We are told that the hill is got a coefficient of static friction. So US is going to be equal to 0.1. And our coefficient of kinetic friction is going to be 0.05. We shouldn't end up needing static friction because we are moving throughout all of this. We are also given that the mass of A is equal to, well, let me find it here, I'm sorry. Mass of A is, I have to pause this just because I can't find the silly number. Mass of A is 70 kilograms. And the mass of B is 120 kilograms. So we have our 2 people at the top of the hill going down. And we have been asked for a few things. We are asked, or what defines are, we are asked for the times, who makes it to the bottom first. We call it who makes it down first, which is hence asking us what the time to the bottom of A is and what is the time to the bottom of B. And we are asked who goes further. And for that, we are more or less asked after we hit this bottom, we're assuming the velocity is the same. So that whatever velocity we have going this direction becomes the same velocity going straight. A little bit of a weird piece, but we're going to go ahead and assume that we have no loss of velocity as we change direction here. So we're asked for the distance, so we'll call this D. So we want to know what the distance of person A is and what the distance the person B goes is. Okay, let's get started. I am going to start with person A. And how I'm going to start is I'm going to do this first portion of the problem first, and then I'm probably going to have to pause and erase everything, and then we'll go to the second one. So let's do our free body diagram of person A on the hill. Okay, so person A is sitting at this angle. they have a gravitational piece, and gravity always acts straight down. So this is mass of person A times gravity. They are going to have a frictional force. Friction acts in the direction of resistance to the direction of movement. So you're sliding down the hill, friction is going to be pulling you up. We don't have anything pulling us or anything. However, we're not falling through the hill, which means that we need a normal force. And the normal force is always going to be perpendicular to the surface. And here is our problem. We have the issue that we have dimensions that are not all lining up perfectly with our two axes. So how are we going to deal with this? We're always going to want to have our friction and our normal force along axes. That is going to make our lives the easiest possible. So we're going to call positive x our distance down the hill, and we're going to call positive y our distance above the hill, so our diagonal distance out here. And that means that I'm going to have to break out this piece, this gravity, into two pieces. So I have mass of A times gravity, and this would be in the y direction. And this would be mass of A times gravity in the x direction. And if I go through and I do this for the free body diagram, I don't know why that's really weird. I'm going to erase it. We have free body diagram of B on the hill. It's going to look 100% exactly the same. They're on the same place. They've got the same forces acting on them. We've got a normal force. We've got friction. We have mass of B times gravity now. But all it changed is I changed the little letter from an A to a B. So I've got my dotted line there, my dotted line there, this being mass B times gravity, the portion of that that's happening in the x, and this is going to be mass B times gravity, the portion acting in the y. And we got two free body diagrams. They're exactly the same, but we got the two free body diagrams. So let's go ahead and try to solve this. I'm going to go ahead and put this right here. Ooh. Now we'll deal with the fact the black square is in the middle of it. We have my x-axis and we have my y-axis, and let's talk about A. So normally when we go about these, we try to solve for our normal force so that we can get our frictional force, because otherwise we can't get to it. So I'm going to go ahead and start with the y-axis. So my sum of forces in the y is going to be equal to my mass times my acceleration in the y. And this is really why we set downhill to be perfectly in the x, because now I am not going up or down. I have no acceleration in the y. This whole piece can go out, and that makes my life so much easier, just getting rid of an unknown from this entire equation. So my sum of forces in the y, I have a normal force acting in the positive direction, and I have my portion of my weight that is pulling me towards the surface acting downwards. So this is mass of A times my gravitational piece times, well, this would be, this is my angle, this is going to be my cosine, cosine of 30 degrees. Okay, I'm going to tangent a little bit here, and we're going to talk about why this is cosine so that people are all on board with it. So in order to do that, I'm going to draw my whole system as big as I can here so that we've got some room to work with stuff. My system is at an angle of 30 degrees. I have a 30-degree slope on this hill. At the top of the hill, I have my rider. I guess I can draw him as little guy on a sled. He has a mass force that is acting straight down. So this is that mass times gravity. If I continue this, this ends up being a 90-degree angle because this is flat, that's straight down. And a triangle, all of our sides need to add up to 180 degrees. This is 30, this is 90. That means this guy has to be 60. Okay? Now I wanted to use 30. So what I did for the 30 is if that's 60, this whole thing has to be 90, meaning this has to be 30 degrees. I'm sorry, I've erased a bunch here, and it's wet, so the markers are not writing quite as well as we would hope. So if that's 30, I'm going to go ahead and kind of draw a zoomed in portion of this. And we're going to switch pens and see if that makes my life a little bit better here. I have this portion, which is going to be, I'm going to dash line, this is the force gravity in our y-axis, because we said y is this way. And then we have our actual line, which is right here. And this is our actual force gravity. And then this portion right here is going to be force gravity in the x. And we said from that angle, you saw how I moved it up there. We said that this angle is 30 degrees. Okay? So FG in the x is 30 degrees, and it's the opposite side, so it's going to be sine. So that's the x, and we did the y here. This is force in the y. Force G in the y is going to be the cosine, because it's the adjacent side. So probably looked pretty quick when I just jumped to that. Maybe you want to go through and draw it out. Get used to it. We're going to do a lot of problems with the blocks here. I will say that not every time. This is a common issue people do. People are always assume, well, it's always going to be cosine for the y, it's always going to be sine for the x. It really depends what angle I give you, because I can give you different angles and that will end up putting it as different sine or cosine. You really have to understand the trigonometry and how to follow that through in order to solve that. Okay, now that I've completely tangented, I'm going to go ahead and come back and talk about my piece here. So I have normal minus MGA in the y. Those are the two pieces happening in the y, and this is all going to be equal to 0 because we already said this was equal to 0. So we have normal going up, we have mass times gravity going down. Technically up, remember, is this way. We're drawing our positive y this direction. This is positive and positive. We set our axes in those directions. So I can actually use this and I can solve for my normal force is going to be mass A times gravity times cosine of 30 degrees, which is going to be mass A is 70 kilograms times 9.81 meters per second squared times the cosine of 30 degrees. And that comes out to 594.70 newtons. Boom. There we go. have our normal force, we can now move and we can talk about what's happening in the x. I'm going to stick with green. So I have my sum of my forces in the x is equal to my mass. This is still working with A, that's why I've got it in green, times my acceleration, times my acceleration in the x. And now, well, I am accelerating down the hill. I do want to start going down the hill, so I should have an acceleration there. I can't get rid of that. It was really nice that we could get rid of the y. So I have, in the positive direction, well, I've got the portion of gravity pulling me down, so I've got my mass of A times my gravity times sine of 30 degrees. And then counteracting that, I have minus friction. And you will write it as friction the first time, is going to be equal to the mass of A times the acceleration of A in the x. So with that, what I get is I have, I'm going to go ahead and break out the friction here. MA times G times sine 30 degrees minus mu K. I'm moving. I should be using kinetic friction. Times N is equal to mass A times acceleration in the x, and I'm trying to solve for my acceleration because I'm asked who makes down first. I need to have something that I can move to kinematics because we don't have any time in the sum of forces equal to the MA equation. So I'm divided by mass of A, and what that is going to give me, mass of A is 70 kilograms. 70 kilograms times 9.81 meters per second squared times the sine of 30 degrees minus, I'm going to go over the line here just because of space, mu k is going to be 0.05. We've got low friction for our ice and snow that we're moving across, times 594.7. All of that divided by 70 kilograms is going to be equal to acceleration in the x is equal to that. And that all shows up as acceleration in the x. I get a value of 4.48 meters per second squared. Whew-da. And this is where this gets long, because I'm going to take that and I'm going to keep working in the x. I'm going to go ahead and erase all of this. I want to know how long it takes to get to the bottom. Well, I've got a kinematic equation in the x that says that x final is equal to x initial plus, don't like how wet this board's getting, velocity initial in the x times time plus 1/2 acceleration in the x times time squared. And I want to solve for time. X final, well, I go 100 meters. So that's 100 meters. X initial, we're starting at 0. We're going from 0 to 100. I already said my velocity is 0 at the start. Plus 1/2. My acceleration is 4.48 meters per second squared times time squared. Can now erase this guy, no problem. Okay, and with that, I have 100 meters times 2 divided by 4.48 meters per second squared. I'm going to take that entire thing, find the square root. That is the time it takes me to get down to the bottom. And that time comes out to 6.68 seconds. So time, where can I put it? Time to the bottom of A is going to be 6.68 seconds. And while I have, we'll come back to it. So with that, go ahead and give me a second to actually erase this board well, and we'll get on to B. Okay, I know that's not great, but that's about the best I can do, unfortunately, with this board. So it's still going to be a little bit wet, but let's go ahead and start on B. So for B, the setup is going to look a whole lot the same, other than I'm doing it in blue. I have my X, I have my Y, I start with my Y. With the Y, I have sum of forces in the Y are equal to my mass times my acceleration in the Y. This is mass of B. I have no acceleration in the Y because I defined it such that all of my acceleration is going downhill. So this is equal to 0. My forces, I have a normal force up, and I have a minus mass B times my gravity times my cosine of my 30 degrees. It's still the same hill, it's still the same angle, is going to be equal to 0. I plug all this in and I solve for my normal force. My normal force is going to be equal to 120 kilograms times 9.81 meters per second squared times the cosine of 30 degrees. And that number comes out to 1019, so 1019.49 newtons. Simple enough. That's exactly the same as I did on the other one, just change the numbers. I now am going to move it to the X. Sum of my forces in the X are going to be equal to mass of A, because I'm sorry, not mass of A, mass of B, because I'm looking at B, times acceleration of B in the X, which is not 0. Again, all of our acceleration is in the X direction. So sum of forces is going to be, I have my mass of B times gravity times now sine of 30 degrees. So with that, I then subtract my friction. I'm going to go ahead and straight up write it as mu k times my normal force is going to be equal to mass of B times acceleration of B in the X. Great. Plugging everything in, acceleration of B in the X is going to be equal to the mass of B, 120 kilograms, times 9.81 times the sine of 30 degrees. All that minus mu k, so that is 0.05 times my normal force, 1019.49 newtons. All divided by my mass, which was 120 kilograms. Acceleration of B in the X, well, that comes out to exactly my same number, which I don't remember what it was. Acceleration of B in the X was equal to 4.48 meters per second squared. I am accelerating at exactly the same rate as student A was. Even though I weigh 50 kilograms more, I weigh almost 100% more than them. Maybe not almost 100, but I weigh significantly more than them. I'm getting close to double. Now with this, why is this happening? Well, what's happening is if you look at what my equation for my normal force is going to be mass B times gravity times cosine 30. If I plug that in here, I note that I've got a mass B in this term, because it's right there. I've got a mass B in this term, because it's right there as part of the normal force. I've got a mass B here. If I divide everything by mass B, it just comes out of the equation. It ends up being exactly the same. It is the mass of the person is not actually playing any role in how fast they're going down. Everything comes out of the equation. Now I will, for sanity's sake, go ahead and write it out again for my time, just to show that in the same way as the acceleration didn't change, our time didn't change. Should be hopefully fairly obvious to you because the mass doesn't show up anywhere in our acceleration equation. In our kinematic equation. So x final is equal to x initial plus v initial in the x times t plus 1/2 acceleration in the x times time squared. X final is 100 meters. X initial is 0. Velocity initial is 0. Acceleration is 4.48 meters per second squared. Time squared, if we solve this whole thing for time, not going to write that out exactly again, I get 6.68 seconds. Time to the bottom of B is 6.68 seconds. Who's going to make it to the bottom first? Nobody. They're going to make it at the same time. Okay. Let me clean up the board, and we will start on the second part of this problem. Okay. Clean board. With this, who goes further? We determined that they're both making it to the bottom at the same time. Who is going to go further? First thing we're going to do is we're going to look at our student A again. And what we're going to calculate here is we're going to figure out, I said the velocity at this angle is going to end up being the same as the straightaway in order to solve this problem. That's how we're doing it. We're assuming that that is true. So what is that velocity? Well, in order to find that velocity, what I'm going to do is I'm going to use my velocity equation. Velocity is equal to final is equal to velocity initial plus my acceleration times my time. Because I have all these values, my velocity final is what I want. My velocity initial is 0. I'm not moving. My acceleration is my 4.48 meters per second squared, and my time is my 6.68 seconds. And that gives me a velocity of 29.93 meters per second. That is my velocity at the bottom of the hill, which is the velocity that I assume I have going straight. Now, how is it going to slow down? We're going to need a new free body diagram. I probably would have drawn both of these up front, the exception being when I'm working on this board, which is tiny, and I knew I was going to need the space. So let's draw it now. In this case, I have my object here. I have mass times gravity. This is mass of person A times gravity. I have a normal force acting up. I have a frictional force slowing me down. Do I have anything pushing me forward? Nope. I just have the continuation of my previous velocity. So this is everything in this free body diagram. So this is the free body diagram for A, and I will draw it, but what you're going to find is the free body diagram for B, just like before. is exactly the same. All we're doing is we're changing the little subscript from MA to MB because we've got different masses. We have exactly the same free body diagram going on there. And this is a lot nicer because for these, we just say this is positive y, this is positive x, and everybody's happy. And this problem should be something you could solve based off of the last example video. So from day 8, we were doing things like this. So what we have to do is we're going to go ahead and split up. I'm going to go ahead and erase part of this just for space. I'm going to go ahead and split up my x and my y. I'm going to start with the y because I need the normal force in order to actually solve for this friction. So I have sum of my forces in the y is equal to mass times acceleration in the y. I'm not going up or down, so acceleration is 0. Sum of my forces, I have a positive normal force. I have a negative mass times A times gravity. Isn't it nice when we don't have a sine or cosine there? My normal force is going to be mass of A. Mass of A is 70 kilograms. Times gravity is 9.81 meters per second squared. My normal force here is going to be equal to 686, I think 686, yeah, 686.7 newtons. And that means that I can grab that normal force and I can start solving for my x. And sum of forces in the x is mass times mass of A, because I'm working with A, acceleration in the x. Acceleration in the x is not 0 because we're moving in that direction. We even know how fast we're moving in that direction. So sum of forces is, well, I have a negative friction in the x and I've got nothing more. So negative friction is equal to my mass of A times my acceleration of A in the x. I can go ahead and say that this friction is mu, negative mu k, because I'm moving, times n is going to be equal to my mass of A times my acceleration in my x. Acceleration in the x is going to be equal to negative mu k, which was 0.05, times my normal force, which was 686.7 newtons, divided by my mass of A, which was 70 kilograms. And that number comes out to be negative, which is good because we got a negative there, 0.49 meters per second squared. I'm going to go ahead and put acceleration in the x is equal to negative 0.49 meters per second squared up here, because we'll erase this once more. And we will look at what's happening in kinematics. So once again, we want to know how far we make it, or I guess in this case, XF, we're going to go ahead and call my distance final. What is the total distance I'm traveling? My distance final is going to be equal to my distance initial plus my velocity initial times my time plus 1/2 my acceleration times my time squared. Ruh-roh, I don't want to have to solve that, because in this case, I want distance final, I have distance initial, I do not have I have my v initial, I have my acceleration, I do not have time, so I have two unknowns. So I could go ahead and use that. Let's see which way I solved it. I didn't solve it this way. Okay. I could use that my v final is going to be my v initial plus my acceleration times my time. And I have my v final. So I've got my, this wasn't v final anymore. This is v initial now. This is the velocity right here. So probably should be careful about final versus initial, but this is v initial because the v final going down is the v initial going forward. So I have my v initial. I'm just going to erase that. And I have my acceleration. I could figure out how long this is and then plug the time in up there. I'm going to go ahead and skip the step and write our third kinematic equation where we say that my velocity final squared is equal to my velocity initial squared plus 2 times my acceleration times the change in my distance. So d final minus d initial, which is just the distance I went. So I'm just going to leave that as d because that's what I'm trying to solve for. I want that total distance traveled. So v final, well, I want to know how far I go until I stop, which means that in order to stop, I better be at 0. V initial is this 29.93 meters per second. I got to square that, plus 2 times my acceleration, negative 0.49 meters per second squared, times d. D is going to be equal to 29.93 meters per second, this whole thing squared, divided by 2, divided by 0.49. So person A is going to go a total of 913.95 meters. Woofda. So distance traveled by A is 913.95 meters. You may have already figured out what distance for B is, but we're going to go ahead and prove it. Okay, it's not terribly clean, but hopefully that gave enough time to dry. With this, starting on B, we have our X and our Y axes. If we go and look at our Y axis, we again have sum of forces in the Y is equal to mass of B times my acceleration in the Y. We're not going up or down, so that's 0. Sum of forces, we have a positive normal force and we have a negative gravitational force. Our normal force is equal to our mass of B, which is 120 kilograms times 9.81 meters per second squared. That comes out to be 1,177.2 newtons. I can then solve for everything in the X. Sum of my forces in the X are going to be equal to the mass of B times my acceleration in the X, which is not 0. Only thing going on here, once again, is my friction. And I can go ahead and say that my acceleration is going to be equal to my, my friction, which is mu k. So mu is 0.05 times, mu k times n times 1177.2 newtons. That's negative, divided by my mass B, so divided by 120 kilograms. This all comes out to be an acceleration of negative 0.49 meters per second squared. which is exactly the same as what we had for person A, because once again, everything has, so this friction is UK, which in this case, my mu is my mass. UK times N, and my normal force has my mass in it, and that's going to go ahead and knock out mass from the equation. It's not dependent on mass. We will find that dB is equal to 913.95 meters. The weight of the person does not impact how far they go. Great. Take care.